Hey everyone, I'd like to welcome the CVPR community to our garage at Kodiak Robotics in Mountain View. My name is Andreas Wendel and I'm the VP of Engineering at Kodiak. I've been part of the computer vision community for more than 10 years now, and I've spent the last 7 years digging deep into various areas of autonomous driving. 5 years at Waymo working on surface street driving, and 2 years here at Kodiak working on trucks. This is my second talk at the CVPR workshop on autonomous driving. As maybe some of you remember, I gave a talk on high-quality traffic light detection a few years back while working at Waymo. With all of that out of the way, I'd like to get all of you into one of our trucks today and take you on a ride that resembles our daily operations. All of us have seen video snippets of autonomous rides, and some were fortunate enough to be in actual autonomous cars, and even fewer in fully self-driving ones. Not so many have been in an autonomous truck though, and I want to give you an impression today what it's like, why we at Kodiak think it's the right product to launch in the autonomous driving space, and what some of the real-world challenges are. In other words, I want to show you some of the things you usually don't hear about when talking about autonomous driving. Before we get inside, let's take a look around the garage. What does it actually take to build a self-driving truck? Of course, we need the truck itself, and it already has steering and braking. But neither of those are by wire in a truck, meaning that we have to install actuators that let us control steering and braking. And we have to get those redundant eventually because we never want to lose control of our truck. Then, of course, we have our sensors and our compute system that is essentially the brain of the driver. We'll get into those in more detail a bit later, but again, we don't want any single fault to cause the self-driving truck to stop working. But that's easier said than done. Imagine your main computer going down. You still need to be able to safely pull the truck over. That requires supporting systems such as solid power distribution and a communication framework which need to be redundant and error-free. All of those systems currently cost a lot of money. But given the price tag of a truck, it's a much smaller percentage compared to a passenger vehicle. Finally, there's another major component for now, the safety driver. This person needs to hold a commercial driver's license to drive a truck and needs to be in command of the vehicle at all times, even if they're not driving. So let's hop inside and see what it's like in there. We're now inside one of Kodiak's autonomous vehicles, and you can see the view an engineer riding in the truck would have. We have remodeled the cabin to have additional seats in the back where usually the bed is, and we have added a very minimal interface to the driver on the dashboard. He or she can see a colored light indicating the autonomy state, hear audible warnings of state transitions, and interact with the vehicle using the regular pedals and steering wheel buttons. Our team is currently running disengage checks to make sure that all ways of taking control of the vehicle work correctly. This is important to make sure any testing is safe, and safety is our most important value. It comes first and is always on our minds. Safety is not a standalone project or department, but instead something that must be ingrained in our culture. Every employee needs to be an advocate and understand and challenge the safety process during their development. Every employee can ground our fleet to review a safety concern, and everyone has a voice in our frequent safety meetings that several members of our executive team attend regularly, including me and our CEO, Don Burnett. So we're done testing the system now, and we will head out on the highway. While we wait for a load to haul, let me tell you a bit more about Kodiak's business case. We're building autonomous technology for what is called the middle mile, meaning the long stretches of mostly highway driving between cities or between various logistics centers. On these stretches, Kodiak operates directly as the carrier, meaning that we are building a logistics company that transports the goods autonomously. On the first and last mile, human drivers bring those goods to transfer hubs, where we swap the trailers. Of course, the picture that you're seeing here is not really up to scale. It looks more like this one. The first and the last mile are very short, and the middle mile is very long. Even today, we operate several trucks on such a shipping lane in Texas, between Dallas and Houston. So why not build the full experience, ramp to ramp, depot to depot? The problem is not the technology itself, but actually building a safety case around it in urban environments. Having been at Waymo and being part of the first driverless launch, I believe most people underestimate how difficult it is to build such a safety case. So at Kodiak, we want to make the problem as simple as possible to start with, while being absolutely safe. We're now at our transfer hub, and our load to haul is incoming in a manually driven truck. Doing the trailer swap is fairly easy. Let's watch this for a few seconds. You can see the manually driven truck pull away, and we have our autonomous truck back up and attached to the trailer here. Our operators make sure that the trailer is safely attached, and now we get in and we're already engaged. So we're heading out to the highway. You can see that the green light on the dash shows up as green, showing us the engaged stage. And after a few merges and lane changes, we're on the highway and start driving towards our destination. Let me pause here and talk about the first technical feature, merging. We did a few merges already, and there's many more to come. Basically, at every on-ramp where other traffic merges in. And if you look at the image here, those are not simple situations, and they are very different in a truck than in a passenger vehicle. What should we do here? We're looking at the vehicle in front of us with about 5 seconds distance, and we have several vehicles on the on-ramp to the right. In my own car, I would lane change to the left, but look closely. There is another vehicle in our blind spot. Can we speed up and lane change that quickly? That's not that easy in a truck because of the weight and size constraints. Also note that the weight and length often change based on the load we're delivering on a given day. Maybe we should just wait and see what other vehicles do. That's not that simple either, since trucks can't decelerate quite as much as passenger cars can. To assess this situation correctly, we need to know the speed and acceleration of the other vehicles well. This is my first takeaway. Object detections and tracks are a great start, but you really need more than that. You need speed and accelerations of those tracks to do well, and that in turn requires a very good tracker. I also want to mention that this is a typical situation where a driver at Kodiak would disengage. Why? Not because they have to, but because they want to do everything possible to keep us safe. We can take this instance and create a scenario from it, where we then go and check what would have happened. That's much better than letting it ride. But of course, it's also something that affects your metrics, which is why, and this has come up several times recently, miles per intervention, or MPI, on its own is not the right indicator for the performance of an AV. So let's just do that and look at the simulation that we created here. This is imported directly from the log to be realistic, and you will notice some of the sensor noise because of that. More importantly though, we see the safety driver's reaction of slowing a little in yellow, and you see our truck in red that is much more assertive in claiming the gap. Then it backs off though and increases the following distance. Both seem acceptable behaviors in this case, and we can lock the scenario in to test for regressions in the future. It doesn't stop here though. We can now move the vehicles that were there in reality and create variations of the same scene to challenge our system, all without going out and driving again. This is most useful for improving our planning and prediction stack. We can run hundreds of variations, which will often find edge cases that need fixing. If needed, we can even go one step further and render the full scene as you see in this picture. This is most useful to test our perception system, since we can modify sensor locations as well as appearance of the objects and the environment, including the weather. In contrast to what many believe though, this is the simulation that is used way less than its planning counterpart. Compared to regression tests, you would only use this kind of simulation when releasing new classifiers or figuring out sensor positioning, and it is comparably compute intense if done well, and thus very expensive. We're very happy to have such a high quality simulator though, and it enables us in a lot of ways. Now that we have looked at the merge problem, let's drive down the road for a while. This is usually quite easy, as you can see. So this is the highway between Dallas and Houston, and you see a lot of cars passing us, but there's not that much action going on. Here you see a lane change, and that was actually for a vehicle that was stopped on the shoulder by the police in this case. A lot of the perception and planning performance that you just saw in this video is not new. It is built on top of what the research community has achieved over the last few years. From camera-only object detections, such as an SSD or YOLO, to LiDAR-only nets such as point net, voxel net, point pillars, and combinations of the two to use LiDAR and camera together, there has been a lot of progress. Similarly, in other domains such as lane detection and localization, as well as optimization for calibration or planning, a lot of research has led to very robust methods. At this point, I would like to thank the people working in those areas for your contributions. And I'd like to extend my gratitude also to those who created benchmarks around these topics to challenge researchers to go above and beyond. So how do we improve on that to create an actual product? I'd like to point out some challenges that might be interesting for your research too. In many cases, we need to do the typical thing in machine learning: create a good data set, balance it well, and train with the right classes and data. Even though there are way fewer cases than there are on surface streets, there is still a large number of these hard cases that we need to work through. We might see objects in weird perspectives, as on the top left, construction objects, and cars on top of each other because they're towing. We even see pedestrians or fruit stands next to the highway. We'll need to handle all of them safely, even if we don't handle them perfectly. To do that, LiDAR information still helps a lot at the moment compared to image data, because it allows to create backup catch-all systems that make sure you're not actually getting too close to any other objects on the road. Additionally, there's also challenges fusing data across LiDAR, camera, and radar. Look at this example, where a large truck passes us. It's quite hard to see in the images that this is a truck and that it's all the same object. It looks very different. Even looking at the point cloud this close up, it's not entirely clear that this is a truck or even one object. Lots of time goes into cases like this, where you need to get the timing and fusion right to not cause harsh braking. Because sometimes those vehicles actually do encroach on your lane, often due to wind, and then you do need to nudge slightly to avoid a collision. So accuracy this close up is very important. Here's an example where we are tracking a large truck in such a situation, and the tracker does a very good job putting the object together and predicting this cut-in. As we keep going on our ride, there's other interesting cases. Look at this one. The vehicle lane changes here, and that's not for the merging vehicle, but actually for the vehicle on the shoulder. We always strive to pass such stalled vehicles one lane over, or slow down by 20 miles an hour if we cannot lane change. These cases are actually quite common, which was unexpected for me. On a regular Dallas to Houston trip, we see 3 or 4 of them. That's why our sensing system is designed to do well in such cases and use computer vision a lot at long ranges. Here the lane change occurred about 400 meters in advance, and our first detections range back to up to 700 meters. Now that's not always needed, 700 meters, but it definitely helps to improve the comfort of the lane change. So looking at the entire sensing system, laying out sensors around a vehicle well is very difficult. You need to see well close by, but also far away, as we have seen. It's really a science on its own. The large distances you need to cover and the different weather conditions over longer trips make it important that you use the right sensors. We use 360 degrees radar coverage around us and long-range camera coverage, plus long and short-range laser coverage. Our sensors are mostly mounted on the custom-built mirror pods that you see on the right side. We design our sensor mounts in-house and partner with the top sensor suppliers to get high reliability. Here you can see examples how we analyze the potential deformations of any mounts, Of course, the motion is way exaggerated here for visualization. And also we look at any thermal issues. We did this from day one of Kodiak because we think it's crucial. Why though? Let's take a look. Assume we are operating 2,000 hours a year, which is very little for a truck. And we want to have a reasonable probability that we don't need to repair the truck. Then we can use a Poisson distribution to estimate that the failure rate for one sensor needs to be 1 in 4.5 years, operational years that is, so we're using the 2,000 hours for that calculation to achieve that. But if our truck has 10 sensors on it, every sensor needs to get 10x this good. With more sensors, we suddenly need very high reliability, also referred to as automotive grade sensors. Hardly any sensors that have the optical quality that I showed you just before are automotive grade yet. So there is more work to be done there. If we turn this around and look at what is available, then we get about 1 fault in 1,000 hours, so much lower than needed. That means with one sensor, you have only a small chance of having issues in a 10-hour run, but at 20 plus sensors, like some of the robotaxis have, you will have quite a lot of hardware faults purely from sensor lifetime considerations. So how do we fix this? We make our system hardened and tackle the problem from the beginning, including redundancy and plans on how to react to faults like this in the field once they occur. We also chose a business model that allows us to access sensors periodically by being the operator. And finally, we work with our sensing partners in hardening all of those sensors, of course. This can take a few years still, but we feel like we have a strong plan in the meantime. Let's get back to our ride down the highway. We're hitting more traffic now, and we handle it well. Then the truck suddenly lane changes left again, and a bit later, it changes back to the right. Why was that necessary? We actually knew from our map that we're coming up to a large pothole recognized by another truck in front of us, and we wanted to avoid that. Because autonomous vehicles are quite deterministic in where they drive, they have a high chance of hitting this pothole several times a day, and we would affect both the reliability of our truck and we would also make the pothole worse. So how does this work? Here's a graphic that visualizes it in form of a more generic blockage. The yellow semi-transparent truck is the first truck that does not know about the pothole and will perceive it late and go around it slow. Or, like many human drivers too, it would just hit it the first time. Once we know where it is though, we will be able to update our maps automatically within minutes and avoid it the next time, which is what the red truck is doing and what you have seen in the video before. A key component to make this work is that we build and maintain our own maps with a thin localization layer on top, rather than building expensive and highly manual HD maps for every place that we drive in. We believe being able to update our maps quickly is a big advantage already, and it will enable us even more in the future. We have now arrived at our destination, another transfer hub, and we will swap trailers again. You can see us take the exit here and pull over. The autonomous truck can then turn around and do the opposite leg of the shipping lane. On our lane between Dallas and Houston, we have been running daily deliveries for Fortune 500 companies for a few months now, and we're excited that we can combine those operational learnings with AV testing time. That brings me to a final question that I hear a lot. How many miles are needed to launch? At Kodiak, we believe that it's not about accumulating the maximum number of miles, and there are good reasons for that. What you want to see to build a safety case depends on the operational design domain, or ODD. The more narrow the ODD, the easier it is to validate with less miles. You will also want the final sensor setup in place. So we're currently not counting on our miles as being validation miles. When you change your sensors significantly, the clock starts again on most of your validation miles, because the data set you evaluated on before is not representative anymore. That's why we use a systems engineering approach with 3 components to optimize our learnings. We drive comparably few on-road miles, but they're very much needed to discover properties of a shipping lane, such as, for instance, at the moment, love bug season, or making a Texas exit. Look it up if you don't know it. They also teach us a lot about our business of logistics. Of course, we drive a lot of miles in simulation, and we continuously extend our datasets with scenarios for new features and scenarios that prevent future regressions. Finally, we use structured testing on closed courses to verify and validate requirements, as well as to stage rare events that we don't want to test on public roads, such as recovering from getting very close to other vehicles. To wrap up, I hope this talk gave a slightly different perspective than what you usually get at CVPR. I'd like to give you some thoughts on what I personally think is key to building robust approaches and eventually launching autonomous vehicles. First, we need to constrain the problem and know when we step outside the bounds. At Kodiak, we are cutting complexity where we can. We drive on the middle mile as the operator. We focus on trucks, and I hope you have seen today that trucks are quite different than passenger vehicles. We'll only drive the miles we need. We'll start in Texas where the weather is favorable, but we have to detect changes in the weather. We will also need to know exactly when our trucks is not good enough to head out and deliver a load. That could be because a sensor does not work properly, or because major roads are closed. This is difficult to even detect and important to plan for from the beginning. Second, to get a product in AV, you'll need to handle uncertainty in all components and think about how you fix the last few percent that you're not doing well at. So getting all parts good enough, rather than getting some of them perfect, is important. In a classifier, a few percent more don't matter as much as how badly you fail in the other cases. The more edge cases you can catch with one approach, the better you will do overall. That's not how research metrics are set up today, so it might be something we can work on together. Finally, being safe in all respects is top of our mind at Kodiak, and we believe it even makes us move faster, because we, for instance, get great simulations triggered by preemptive disengages. We have groundings that put focus on particularly hard issues, and our strong safety culture where everyone can speak up really brings the team together. I hope you have enjoyed this talk and see that Kodiak is uniquely positioned to tackle this problem with our background and team. We do celebrate our successes together, as you can see in these pictures, and we would love to have you join us for the next celebration. Thanks, and take care.